All right, so we will continue this discussion on the durability aspects in reinforced concrete design. So this is the fourth lecture as part of this module 3. And in this video, we are going to discuss about what is the design approaches that the codes they use, and we'll compare also the code provision that are existing in IS 456 and IRC 112 and Indian Railway Standard provisions. Okay. Right. So the expected learning outcomes from this lecture is the student should be able to list out different durability design approaches. We have a couple of them, and also we can have a hybrid approach. We'll talk about that. And the student should also be able to understand the need for performance-based durability design, and and should be able to define what is the durability index and their requirements, and students should also be able to understand the importance of mixed design in performance-based design and compare the provisions, especially the durability provisions in different codes. We're going to focus only on the Indian codes of practice. Right. So we have seen this in the very first part of this module. For resistance to corrosion mainly depends upon how good your impermeability of the concrete is, and also how good the quality of cover, because that is basically like the gate which is going to allow the entry to this deleterious substances. If your concrete is very dense and if it is going to be very robust, then your corrosion resistance will also be better. And in terms of load, it comes from aggressiveness of the environment. How that could be in the coastal region or what is the marine condition. All this thing will play a role. So we talked about this in the very first part of the lecture. Concrete system has intrinsic factors and extrinsic factor that will determine how good your concrete system from durability point of view. And intrinsic factors include what type of cement and what is the chemical composition of cement, what is the water binder ratio, and what is the quality of aggregate, admixture, and so on. And similarly, extrinsic factors include how good you mix the concrete and how good you place them and how well you compact them and how well you cure them. In environmental conditions, we have two aspects: physical deterioration and chemical deteriorations. We talked about that in the previous parts of the module. So all these things combinedly will determine how durable your concrete is. So that is what we need to be careful about. Okay, right. So let's see what are the approaches currently available for durability design. Okay, so if you see currently, even including our IS 426, these are all prescription based. So if you follow the provisions that are given in the code broadly in terms of concrete composition, what should be your maximum water cement ratio, what should be your minimum cement content, and if you satisfy the cover requirements, you are assumed to have that you have satisfied the durability design requirements. Okay, that is what it's prevalent now, which is a perspective. uh, it's actually prescriptive based. It's not perspective, it's prescriptive based. Okay, and the another one is the performance based. It depends upon the performance requirement of the structure. So here the approach is to avoid deterioration. Here in performance based durability design, okay, or serviceability for durability, what we do is we design resistance to tackle the deterioration. And here the service life is not really specified, it is assumed. If you follow all of the prescriptions, then your structure is deemed to satisfy the durability requirements. But here you are specifying a particular service life, and for that particular time, if you look at it, you are also guaranteed what is the acceptable level of deterioration. And here the durability is assumed, and here we are designing for durability, right? So sometimes we can also, it's very difficult to implementing performance based durability design. We can also take a middle approach, which is a hybrid approach. Some provisions can be prescription based, some provisions can be based on you design for a particular performance. Okay, so you can also follow a hybrid approach. Right now, let's look at how do we do this performance based approach for durability design. For any project, the location of the structure will be given, right? So the moment you know the location of the structure, then what we can do is we can go ahead and assess and characterize how aggressive that particular exposure environment is. And if you look at this IS 456, we depending upon where the location of your structure is, though it's not very detailed, but at least it gives you an idea what kind of environment that particular structure is subjected to. For example, mild environment, as per IS 456, we know that concrete surfaces are protected against weather or aggressive conditions. But if you look at extreme environment, here we have surface members that are in tidal zone and members are in direct contact with liquid or solid aggressive chemicals. Either you have an industrial structure which is directly contact, or you have members that are correct in the water. Okay, so this is an extreme environment. So depending upon where your structure is, you can also classify what type of environment. So that's what next step is. Then we have to identify what is the dominant mode of deterioration. So we have talked about various deterioration mechanisms in the previous lectures. So, for example, if your structure is having located in marine environment that is subjected to chloride-induced corrosions, then we can select a particular equation or a service life model that is going to give me what is the extent of your chloride penetration at any point of time t. Okay, and x is your depth. So based on these kind of service life models are available depending upon what deterioration mechanism is going to be dominant mode of deterioration. But then once we have the service life model, then we can design and specify what should be the cover depth to tackle corrosion and what should be the binder type and what is the durability index values. We will talk about durability index values. Yeah, they are measured from oxygen permeability or sorptivity test or from RCPT values. So each of them, some codes give you some acceptable values. Using that, we can define what should be the durability index value that we need to design for. Now, so one is usually before we do the construction, of course, the concrete mix design and samples have to be tested in the lab. So we have to do that. And what are the properties that we control for is fresh properties. The concrete should be workable and also it should satisfy the durability index values that are specified by the code. And of course, the strength is a very important characteristics that also should satisfy. So this is what we do. If at the before construction itself in your mix design, if it is not satisfying these values, of course we go ahead and change your, for example, mix design, or you choose a different cement, or you adjust your proportions so that you are able to meet all this fresh properties, durability properties, and strength. Now, once you are satisfied, then you can go ahead and do the construction. And then in construction, of course, you have to mix the concrete well, and the cover depth has to be exactly, follow the structural drawings. So, structural drawing, if it says 50 mm, exactly in the field also, it has to be 50 mm. And it has to be compacted well, and it has to be cured well. And another important aspect in performance-based approaches, you have to have a mock-up structure or samples that are prepared close to that of what you're doing it in construction. Or best is to take samples from the as-built structure and then do the testing. And again, testing, what kind of testing we do for durability and strength. And if it is accepting, if it is acceptable, the values are acceptable, then you go ahead and say, okay, the structure is performed well. And if it is not meeting the norms, then either you can go for remedial actions like applications of coatings to tackle ingress of deleterious substance, or add some corrosion inhibitors later for even as-built structure, and recommend regular inspection and monitor the deterioration mechanisms. Or if it is the results are too bad, then you can also go ahead and reject the structure either partially or completely. We may have to either demolish or reconstruct to a desired specifications. This is what we do in performance-based approach. Now, what is the durability index? Mix design also, if you want good durable concrete, again, you have to pay a lot of attention in your concrete mix design. So let us see. We have to basically contextualize the durability requirements. We should also play play a lot of attention. Pay a lot of attention to mode of deterioration. Either the corrosion is going to play a major role, or abrasion, or sulfate attack. We have talked about sulfate attack also in the previous parts of the video. And you know that the foundation, if it is sitting on a sulfate rich soil, then sulfate attack will be a major deterioration mechanism. So that we need to clearly understand what kind of deterioration that particular structure will be subjected to when it is built in a particular environment. And the understanding also of what ingredients that affects the durability requirements. So that also important. For example, we know that the moment if you are able to lower your water cement ratio, then you will get better performance from durability point of view. Similarly, what type of cement that we are using. Okay, for example, to tackle a sulfate attack, we have to go for cement content with less C3A or sulfate resisting cement, right? So, and also the aggregate type. If you have abrasion or erosion kind of issues, we know that we need to use hard, a good quality aggregate with a very good bond between aggregate and cement paste. Similarly, the kind of admixture that what we do and relevant testing. Okay, and usually these are the three common tests that are recommended. One is the oxygen permeability index to measure the carbonation CO2 penetration, and chloride conductivity test to either we do RCPT test or some test to see the chloride conductivity. Another one is the water sorptivity test for assessing the water absorption. Now we can also come up with the index combination of all these three values. Okay, so in that way we can define durability index using all these three indexes also. Okay, so a durability index basically it gives you physical, chemical, and electrochemical parameter that characterize the concrete durability. Okay, so water sorptivity tells what is the water absorption or permeation capacity of the concrete. Similarly, oxygen permeability test will give you the CO2 penetration levels, and chloride conductivity test will give the electrochemical parameters that will tell you how good your concrete is for corrosion resistance, right? And these are powerful means to characterize the potential concrete durability. So this is why it is very important. Right now, mixed design. I think we have talked about this in detail. It's very important to consider the mixed design aspects, and especially we need to avoid. We have seen for tackling most of the deterioration mechanisms, we have seen that using supplementary cementitious materials is going to really help. So it's better to avoid OPC cement and go for a blended cement. And you can see that with the blended cement also, though your initial strength gain may be slightly slower than your OPC based cement. But if you look at the age of 28 days after casting, you can see that blended cement can get either close to that strength what you achieve with OPC or maybe slightly higher also, because you're using SCMs, then you form additional calcium silicate hydrates that will give you get better strength over a long period of time, and that can also help in minimizing the cement content from cost point of view, from sustainability point of view. We talked about that, and then from paste content point of view, and also the heat of hydration can also be reduced. That can lead to lesser shrinkage crack, and also the excessive admixture usage also has to be prevented. Okay, and because again especially the water reduces like super plasticizers are costly, so the cost again will play a role, and again sustainability. So in fact we should also keep in mind that admixtures are used to enhance or modify the property of the concrete, but not really to fix the bad concrete. For example, now there is a tendency for people to go for corrosion inhibitors post concreting, which is not really a good thing. So if you want to have a better corrosion resistance, corrosion inhibitor can be added while you mix the concrete in the fresh state as well. So that is going to give you better performance. Right, again, so from performance-based design point of view, we have talked about durability index values. There are one is oxygen permeability test. Basically, it helps us to measure the resistance to carbonation. So you can see here in this setup, what we do is we send the oxygen and we put the specimen and in a container, and then we supply this oxygen, and then we try to measure what is the outlet of the oxygen. So from this permeability, then we can find out how much is the resistance of the concrete to carbonation is. Okay. So the acceptance criteria are different for specimens that are tested in the lab scale, and then for as-built structure. Okay, as-built structure means you are doing the testing from the sample that are taken from the as-built structure. Okay, so that's why if you see here, You have laboratory concrete, oxygen permeability index values expected to have more than 10. And then for as-built structures, if it is going less than 8.75, that the particular concrete has to be rejected. And if it is between 9 and 9.4, you have conditional acceptance. And then when it is more than 9.4, you can fully accept that particular concrete. You can see that for as-built structure, the values are lesser than what you get it for in your lab measurements. So, because the guideline recognizes that there's going to be a lot of variability when you do large volume concrete in the site. So that is why it is giving you slight leverage of reduced values for full acceptance. Now, sorptivity test, and it is to measure the water penetrable porosity in the system. And again, you can see this is kind of we have this kind of a container, and then we have solutions, and then with the vacuum pump, we try to see how much that water is penetrating inside the concrete, and then we measure the sorptivity. And again, sorptivity for lab scales, you can see that it has to be less than 6, and for as-built structure, if the value is going more than 15, that means that the porosity and permeability is going to be higher. So you have to reject that concrete. And if it is going to be between 9 to 12, you have conditional acceptance. So the different values have been suggested by different codes. So this is one way we measure the porosity. The next one is from corrosion point of view, we do this RCPT test, and that gives us the resistance to penetration of your chloride ions. And you can see, that if the concrete has higher resistance, it is going to have lesser conductivity. That is what you want. We want the electrical resistivity of the concrete system has to be much higher, and we know that resistivity and conductivity are reciprocal to each other. So if reciprocity is, if your resistivity is going to be higher, then conductivity is going to be lower, right? So that is why if you see here, if your conductivity is higher, then you have to reject. So the value that is given here is 2.5. And if it is going to be between 1 to 5, then you have conditional acceptance. And if it is going to be less than 1, then you have full acceptance. For lab value, it should be less than 0.75. Right? So in this way, we can also define a hybrid index based on combining all these three values. Okay? Or you can also say that if it is satisfying, for example, lab scale, oxygen permeability has to be greater than 10, and sorptivity has to be less than 6, and conductivity has to be less than 0.75, then only your concrete is acceptable from durability point of view. Right. So that this kind of a measurable index is going to help the engineer to specify what kind of performance I need to target and what is an acceptable level of credit. So you are quantifying the durability performance, and it also can help the engineer to approve the mixed proportions, and it can also help the engineer to verify the as-built concrete quality. From contractor point of view, now it gives a leverage for the concrete to select suitable mix ingredients rather than just specifying, in the prescript approach, we know that only the minimum cement content or maximum water cement ratio, or for certain mechanisms, some conditions are given. But here, it gives complete freedom for the concrete mix designer to choose mix ingredients and bind a type admixture ratio to satisfy the durability requirements. And it also helps contractor to put adequate quality control measures during mixing, compaction, and curing. And this is the big advantage with specifying the durability from performance-based point of view. Okay. Now, again, designing and specifying concrete durability is not really enough, and good site practice are critical. Again, we kept talking about it. You may develop a good concrete in the lab, but if that mixed design, when you scale it up in the site, if they are not executed properly, then you will have very different concrete in the site. That's why it's very important to test the samples from as-built structure to see whether you are meeting all the requirements. Also, cover. We keep talking about cover, and cover whatever that you are specified in the drawing should be exactly executed. So that also is important. So good site practice are important. So mixing has to be done properly, and concrete cover depth and condition also has to be as per your structural drawing. And reinforcement detailing, we have talked about it. If reinforcements are placed very close to each other and the aggregates cannot really get inside, and the concrete may not be compacted well, and can lead to a lot of uh, honeycombing and other segregation related issues. And again, compaction has to be done properly to avoid voids. In fact, compaction has to be done in optimum way. If you do over vibration also, you'll have segregation and bleeding issues that we need to be very careful. Curing method, again, it also plays a major role. What is the when you commence curing, and what is the duration, minimum duration for which you need to cure? All of them will play a major role in controlling the permeability of the concrete. And verification, this is the most important thing. Most of the time, at least in India, I think a lot of testing is done before construction, but we don't really do testing from the as-built structure. So it's also, we should verify by having a mock-up structure or taking samples from the as-built structure to verify this durability property. So this is also important. Right. So usually the idea is, as a structural engineer, generally we are concerned about designing for safety from structural strength and serviceability point of view, and the durability design is considered as an add-on. Okay. Now, but actually both are interrelated. If there is going to be proper attention is paid to durability design when you are designing structural design itself, then that will be a very good integrated approach that will satisfy both structural as well as durability requirements. So for that, uh, performance based durability design and specifications are required, and that specification not only is sufficient, and we also need to train the human workforce so that we have a skilled workforce, both from design engineering point of view, and also from at site. Also the site engineers have to be trained, and contractors also have to be educated so that they start appreciating these aspects, and the core provisions are needed. In fact, I am told that IS 456 also is undergoing major revision, and we are in a way kind of moving towards performance based durability design. So a lot of these aspects that what we have discussed will be included in this revised IS 456, where you're going to not just use the prescription that are followed the code, and code is also going to give you a lot of options for design engineers to choose a mixed design that will satisfy specific durability design requirements. And the industries also should encourage a performance based design. So, and more acceptability will from the industry is also important. All right. So now let's briefly discuss how the code provisions, especially from Indian codes point of view, how these durability provisions are laid out and how they compare with each other. So, okay, that's what the point is. Now let's first talk about design service life. Okay. Now if you look at Indian Road Congress provisions, and for normal service life recommended is 100 years or more. Okay. So that is what it is recommended. That is for all bridges. The minimum bridges have to be designed for 100 years, unless if it is going to be a temporary bridge, okay, for giving temporary access to road or to for a construction facility, then your service life becomes 10 or less, depending upon your project requirements. Otherwise, unless it is stated, the default design service life for bridges is going to be minimum of 100 years. So you can see for 100 years, you need to design a system that is going to be durable, and it is also going to perform all the structural requirements and functional requirements without degradation or minimum degradation, and without requirement for frequent repair. Okay. And for special applications, again, 20 or as specified by the user, usually for, let's say, old bridge, you're doing a rehabilitation, and then you're specifying only that I need the service life for 20 years. So only in such cases, more other than 100 years are actually done. Or if you're doing a very iconic bridge that you want to last it forever, sometimes bridges are also designed for 200 years. Okay. So it varies, but minimum guarantee for normal bridges is 100 years. Okay. So this we have to keep in mind. Now, if you look at Indian railway standard provisions, again, bridges in sea condition, they are specifying that it has to be designed for 50 years. And bridges in coastal areas have to be designed for 80 years, because they do anticipate that there's going to be a lot of degradation. And bridges in the rest of the India, has to be designed for 100 years. Now let's look at what are the exposure conditions that are specified in the code, and you can see IS 456. We have discussed this in the previous parts of the video also. And when you classify that as mild, where the concrete surfaces are actually protected against weather or aggressive conditions, nearly the same thing is reflected in IRS 1997 provisions also. And you have moderate conditions. Again, I don't want to read. You can see it by yourself. The provisions are nearly same in all the three codes. Okay, and severe when concrete surfaces are exposed to severe rain and alternate wetting and drying or occasional freezing whilst wet or dry condensation. And for concrete that is completely immersed in seawater, actually it comes in severe category. Okay, and concrete that is exposed to coastal environment also comes under severe category. Now you have again, bridge provisions are slightly different, and they are defining that condition as wet or hardly dry or humid or wholly submerged in seawater. So more or less the same that what you have it for. I have it in IS 446 also. But IRS is exactly the same provisions are taken in Indian Railway Standard. Again, very severe and extreme. So we talked about that. So these are the exposure conditions. What we can say is in all the three codes, the exposure conditions are more or less the same. Now, in terms of minimum cement content, you can see that this is one way of ensuring that once you keep a cap on your water cement ratio, and also you're ensuring the minimum cement content. What the code is saying that if your water cement ratio is kept constant, then if you start increasing your cement content, it is expected to have higher strength. So that is why, depending upon the exposure condition, the code is specifying limit on water cement ratio. At the same time, it is also specifying some minimum cement content. Okay. Now, if you can see, the maximum in an extreme environment as per IS 3, minimum content for IS 456 as per IS 456 for an extreme condition is 360 kilogram per meter cube. However, for bridges, IRC code is able to, in fact, it is allowing up to 400 kg per meter cube. You can ask me why there is a small difference, because in bridges they are long span structures. Mostly, they are also pre-stressed. So for pre-stressing, we know that we need higher compressive strength. So that is the reason the code is allowing slightly about 10 to 12 percentage higher minimum cement content is recommended by RC compared to that of IS 446. And you can see here, IRS has three classifications for plain cement concrete, reinforced concrete, and pre-stressed concrete. And you can see here that RCC and pre-stressed concrete here also, you can see that the minimum cement content recommended is going to be higher than what you need for reinforced concrete application. Now, in terms of maximum water cement ratio, and we have seen that by limiting the maximum water cement ratio, we can limit the amount of moisture and water that is available in the system. In that way, we can also ensure durability. So that is why the code is specifying different values for depending upon the exposure conditions. For example, if you are in extreme exposure condition, water cement ratio is limited to 0.4, and if you are on a mild, it is giving you relaxation. We can go up to 0.55. But nowadays, with the availability of good admixtures and super plasticizations, we don't really need that kind of a high water cement ratios to achieve workability. So we can use chemical admixtures to achieve workability. And these are the requirements for again bridges which are always exposed to outside weather. In fact, IRC provisions are slightly more stringent than IS 456, where the maximum water cement ratio is slightly lower than for a particular exposure condition compared to that of IS 456. And minimum grade of concrete, and we have talked about this. When you go to bridges, you deal with very long span elements. For long span elements, usually they are pre-stressed, and for pre-stressing, it is essential to have high strength concrete to maximize the benefits of pre-stressing. So that is why the code is allowing you to have a minimum grade. So that is why if you see for extreme weather condition, again, your code is recommending that your minimum concrete strength has to be at least 45. And another reason is also, if you're going for high strength concrete, it is understood that you achieve high strength by limiting the water cement ratio, which is again going to help you in durability. And also for a particular water cement ratio, if you're increasing the cement, then it is going to give me higher strength. So that is why the code is specifying some minimum grade of concrete from durability point of view. Right. Again, IRS provisions for pre-stressed concrete is even higher. You can see that for extreme weather conditions, it is specifying M50 compared to that of M40 what you have for building applications. Because building applications, we don't deal with long span elements generally, okay, compared to that of bridges. And nominal cover, you can see again, for bridges actually, for moderate, it is slightly higher than what is allowed in your IS 456, because always bridges are exposed to outside uh, environment more than your buildings. And similarly, IRS provisions also, you can see for extreme conditions, you can the cover depth itself is going as high as 75 mm for IRC and IS provisions. Similarly, IRS provisions also you can see for well, they little bit more they categorize for slab, beam, girder, columns, and well and footings. You can see that the cover requirements are higher. And when you say nominal cover, basically we are looking at only the plain concrete to the level of the bottommost reinforcement to the outside surface. That is what we define that as a nominal cover. Right. Crack width, again, in reinforced concrete applications, under serviceability, unless you're dealing with a very special structure like a nuclear containment structure or a water retaining structure, you are allowed to have some cracks under service conditions. Only what we do is we limit the crack width. Okay, so that's why you see here for severe conditions when it is exposed to external environment, you are limiting the crack width to zero point 0.1 millimeter, very small. However, for interior exposure, you can see here when crack width is not concerned, then you can allow to have crack width of 0.3 mm under serviceable conditions. Okay, not at ultimate. Ultimate anyway, you'll have large crack width because ultimate when the structure reaches ultimate, that means that it is going to fail. So at that point of time, you'll have, but we check crack widths only under serviceability conditions. We will talk about when we talk about flexural design for serviceability, how do we check for this crack width. Okay, similarly, IRC provisions also, if you see here, for very extreme severe, and then you are limiting your crack width to 0.22, and you have two categories. Okay, one is pieces concrete with unbonded tendon and bonded tendon, and you can see that crack widths are specified as 0.2 millimeter. And this is from IRS provisions. Okay, IRS provisions for extreme, it has two values, 0.1 and 0.2, depending upon whether the surface is exposed to weather or protected against weather. So when it is say protected against weather, basically you're going to give some coatings and all. So when it is protected, then you can have slightly a larger crack width that is allowed to have under serviceability limit state. Now again, to tackle the chloride-induced corrosions, the codes are also specifying what is the allowable chloride content as a percentage of mass of cement. And you can see here for concrete that is not containing embedded metal or any other material that requires protection, then the code is allowing up to basically 3% mass of cement. Okay, so this is basically expresses maximum total acid soluble chloride content, okay, which are soluble in acid, and they are expressed as kilogram per meter cube of concrete. Okay, so you can have about 3 kilogram per meter cube of concrete for this condition when the concrete does not have any embedded metal. However, when you have reinforced concrete or plain concrete that has embedded steel, this amount is reduced to 0.6. And when you have concrete that is has metal, and if it is steam cured at an elevated temperature or pre-stressed, when you go for pre-stressed concrete, this amount is further reduced to 0.4 kilogram. And this is a 0.4 kilogram per meter cube is amount of chloride that is soluble in acid. Okay, this is the amount. And similarly, IRC provisions and IRS provisions also gives you what is the chloride content as percentage of mass of cement, and you can these values are specified here, and you can see here for pieces concrete is only 0.1 percentage as the mass of cement as the allowable chloride that is soluble in acid. Again, for to tackle the sulfate attack, and we have seen that for to tackle sulfate attack, the best thing is to use sulfate resisting cement. And the code is also giving you what is the allowable concentration of sulfates in soil. You can see, and also it is giving you different classes: class 1, class 2, class 3, class 4, and class 5, like that. And for class 1 type of construction, and where your sulfate content, SO3 content in soil has to be less than 0.2, and then when you take water from the soil extract, then it should be less than 1. So, and in groundwater, when you're using, again, the limits are given. So depending upon and what level that you're looking at, the limits for sulfates are given. And in this kind of class, we can either use OPC or PPC cement. Okay, and minimum cement content is also specified. Similarly, maximum free water cement ratio is also specified. But the moment you go for higher class, which is more prone to sulfate, we are also recommending all this thing. In addition to that, you also need to have protective coating, and also you are limiting your maximum free water cement ratio, and also you're having minimum cement content. In that way, you can tackle the sulfate attack. Okay, so now let's see for freeze and thaw how the code is addressing. And we have seen in the deterioration mechanism, one way to tackle freeze and thaw is by using air in training, and up to 4 to 5% of air can be entrained in the concrete while mixing itself. So when you have a aggregate size 20 mm size aggregate, you can go up to 5% of air entrainment. And when you have a 40 mm size aggregate, and you can limit it to 4%. So that is what the code is specifying. And IRCs tells that you have to protect the concrete from getting saturated, and it also recommends using an air entrained concrete mix to tackle freeze and thaw. And they are also saying that use high strength concrete. So the moment you go for high strength concrete, again, the permeability is going to be low, and it will not let the water to basically ingress. So that is the idea. Now, IRC 112 recommendations for alkali aggregate reaction, let's look at it. It says that we need to use non-reactive aggregate. We also looked at it. We can do petrographic or microscopic examinations to find whether any reactive silica is there in the aggregate or not. So they are recommending using non-reactive aggregates, and they are also recommending to use OPC cement with alkali content less than 0.6% of your sodium oxide. And then for corrosion preventions, IRC provisions are recommending to use galvanized reinforcement or reinforcement with fusion bonded epoxy coating. So when your elements are subjected to high amount of corrosion or chloride ingress or CO2, they are recommended to use galvanized reinforcement or reinforcement with fusion bonded epoxy coating. Again, we talked about that. This is going to increase the cost, and also, especially this coated rebar, you have to be very careful. If you're not careful while doing construction, your coating may get locally damaged, and it can actually aggravate the corrosion. So that is another thing that we need to be careful. And we can also use surface coatings, and such coatings also has some period. Okay, every 5 years, again and again, you have to go for this kind of coating. That does help in increasing your corrosion resistance. And or use of waterproofing membrane over the bridge deck, that can help in making the concrete impermeable. Or during the construction itself, we talked about this in the previous parts of the video also, using controlled permeability formwork liners. So what happens is, when you have these kind of formwork liners are installed, it will allow the vapor to escape and water to go out. So at the finished surface, you will get a very dense concrete. However, again, the problem is these formworks are very costly. And if your structure is again having a lot of corrosion, let's say if you have an existing structure that is already corrosion is initiated, one way to again do some remedial action is to do some cathodic protection by installing some sacrificial anodes, right? Or use stainless steel. Again, we know that stainless steel, because of the high chromium content, it doesn't corrode. But however, the cost of the stainless steel is a big factor. So these are the issues. And again, IRC 112 recommends that for extreme weather condition, your RCPT values has to be less than 800 coulombs. For very severe, it has to be less than 1200 coulombs. For again, for severe, it has to be, it can go up to higher value of conductivity of 1500 coulombs, and so on. Now let's again look at what is the Indian Railway standard recommendations are. They recommend that permeability test is mandatory for all bridges that are located in severe, very severe, and extreme condition. And this permeability test is only recommended for major bridges, not for uh, normal bridges. It's for major bridges. What is the definition between major and normal bridge is defined in your IRC as well as IRC provisions. And you go for this permeability test only for major bridges in mild and moderate conditions, and the depth of the penetration of the moisture from this test cannot be greater than 25 millimeter. Okay, so that's why the code is also specifying a cover more than 25 mm to make sure that even if the moisture is penetrating, it is not going to reach the level of steel to start the corrosion and other issues. And surface coating can be given as per IRC provisions to prevent corrosion. And but however, we need to check these coatings periodically to make sure that they are intact. And in terms of coating, again, they are saying that for superstructure, either you can go for epoxy phenolic coating, or SICRI, Central Electrochemical Research Institute, have developed some coating, four-coat system. We can use that. For substructure, they're recommending a coal tar epoxy-based coating. And for actually no coating is necessary if you're for especially for um, structures, if it is in mild and moderate exposure conditions. Only for superstructure, then we need to go ahead and do for some kind of coating for structures that are exposed to mild and moderate condition. Now, IRCs, there is a IRC special publication also that gives some recommendations for improving the durability. One is, of course, we know that we want to make the concrete low permeable, and low permeability can be achieved by using adequate cement content and using supplementary cementitious materials like mineral admixtures, and also by proper particle packing in the mix design with the help of dense packing of fine particles. And also the sulfate content, they are saying that it should be SO3 content should be less than 4% by mass of cement. So these are the recommendations that are given in IRC SP70. And for chloride content also, again, the limits are given depending upon whether you're dealing with pre-stressed concrete or reinforced concrete, or reinforced concrete in moderate condition. So if you're in moderate condition, of course, the value is slightly higher because your exposure condition is not very severe. And these are all these chloride content is expressed as percentage of mass of cement. So you can see in moderate condition, you are allowed up to 0.3 percentage of the mass of cement that you're using it in concrete. Right. So we had a quick overview of what is the need for performance-based durability design. So brief introduction was given, and how it is going to be advantageous rather than having this prescriptive-based approaches for durability design, and the importance of performance-based design was discussed. And we also briefly compared the code provisions that are there in IS 456, IRC 112, and IRC 1997 for different durability design or performance requirements. Right. So again, though this course is on advanced reinforced concrete design, where we're going to talk about design of elements for various actions, but durability is a very, very significant aspect. And even in IS 456, as I've told you, it is undergoing a major revision where durability is going to be given major impetus, and you have to not only design for strength and serviceability and other limit state durability also, you need to explicitly design so that the structures are going to be performing without much durability issues, and are not requiring more amount of repair. So that is a thing. So we have given a brief overview of various aspects that need to be considered in durability design. Again, if you want more information, so these are some of the references where the material was taken. Again, you can also look at other NPTEL courses that explicitly talks about durability aspects. Okay. All right. So with this, we will end this module 3. And in the next module, we are going to talk about design aspects for axial loads. We will discuss it in the next week. Thank you.